Okay. In this lecture, we're going to talk about noise. What is noise, and then how can you estimate the noise inside the system, including, the mechanical and electrical components. And then finally, what are the methods that you can reduce the noise in the measurement. At the end of the story, a lot of the money that you pay for a sensor is for its noise performance. You want to measure the smallest possible signal in most situations. And as your sensors become better and better, as you move towards those low, small amplitude signals, the money that you have to pay for the sensor to pick them up is proportionally increasing, actually maybe out of proportion. So how do we figure out what are the noise sources in our system, and maybe if you're designing different components of a system, how can we do that efficiently so that by let's say using the wrong amplifier, we are not destroying the noise performance of the sensor that we have. Or if the sensor that we have has a certain noise limit, how do we avoid spending too much on the electronic side if I cannot really get any gains in terms of noise behavior. So that's the goal of this lecture. What is noise? Noise refers to random fluctuations in a signal with a zero mean. So right away that separates it from a whole bunch of different phenomena. So it has to be random. It cannot come from a source. If you have a 60 hertz line in your vicinity and that 60 hertz is coupling into your signal lines and you're seeing that 60 hertz, that's not noise, that's interference. It's not random. Once you see it now, you can actually predict how it will be in the future. So it's not noise, right? Noise has to be random. You basically cannot predict it, and therefore you cannot eliminate it easily. Or you cannot eliminate it because it's random, right? If you cannot predict something, you cannot compensate for it. The other issue is that it has to have zero mean. So a lot of us have been, used different systems, and we know there is an aging issue, right? So usually the system behaves somehow at the beginning, and things start to change as the device or system ages, right? So we call it aging. But that aging usually is not random, right? So let's say it's especially for mechanical systems, you notice it. So something becomes softer over time, or a mechanical joint becomes harder over time or stiffer over time, and it's not changing randomly. So that again is not noise. For a signal to be considered noise, it has to be random and it has to have a zero mean, meaning that if I integrate it over a long period of time, I should, all those random changes should cancel out. Where does it come from? Well, from the thermodynamics point of view, any system where you lose some energy, dissipate some energy, convert some of the energy in your system into heat, has to have that energy replaced by a noise source, so that you're basically not losing heat from your system continuously. If that happens, then the temperature of your system will drop to zero, to absolute 0 Kelvin. And noise is the nature's way of keeping the equilibrium here, right? So whenever you have a dissipating mechanism that in most cases converts the energy into a heat, you have to have a noise source associated with that energy dissipation mechanism. MEMS devices typically operate at the intersection of multiple physical domains. You have mechanical interactions, you have electronic circuits that talk with your mechanical device, you have interfaces to other physical domains. It could be an optical interface, acoustic interface, all sorts of different interfaces. And whenever you have these different energy domains and then the intersections between them, you will have noise sources in each one of these domains that you, at the end of the story, have to account for in order to estimate your overall noise behavior. Types of noises, in most cases we avoid mostly about the noise in electrical domain, but Brownian noise and Johnson noise and shot noise and flicker noise and all sorts of other noises, we'll talk about some of them today, are different types of noise sources that you have to account for. A lot of them are actually in electrical domain. Noise is generated from within the sensor, and therefore, the sensor plus its interface electronics. And therefore, it's an inherent property of the system once it is designed. So you cannot reduce noise by shielding your sensor. You can reduce the interference that way, but you cannot reduce the noise that way. We'll see that your options to limit noise, to reduce the amount of noise, are actually very limited. And in most cases, you have to rethink the design of the system. Now, what are the definitions? Well, let's assume that x of t is your signal. In this case, we're talking about noise. And we are monitoring this signal in time domain. The average of that signal is found from this expression on the left, the mean of the signal. I go and integrate that signal over some t, and if as t approaches infinity, I basically get the mean for that signal. If it is a discrete signal, I just basically add up all the samples and divide it by the number of samples. The variance of the signal is found from this expression. Again, we have seen these in statistics before, where I take this momentarily value of x of t, subtract mu x from it, and square it so that I do not really cancel the signals that are beyond the mean and the signals that are below the mean. I want the differences to matter. So I square it and integrate it over time. As I increase the t or make t approach infinity, I get the variance. If you have a discrete signal, this is how you calculate the variance. Again, you take mu x, calculate the mean, subtract the instantaneous value from that, square it, and add it up. So mu of a signal tells you something about its average, right? How much the signal is, what is the expected value of the signal at any point. Variance tells you how much information there is, how much energy there is, how much variation do you see around that mean. Small variance means that the signal is very close to its mean. A large variance means that you have large deviations from the mean over time. Now, if I combine two signals, x of t and y of t, with each other, with some weights, axt plus byt, then I can see that the mean of the new signal is basically the combination of the two means of mu x and mu y with their corresponding weights. And sigma z, the variance of my new signal, is given by that expression. So I get a squared sigma x squared, b squared sigma y squared, plus this term, this cross-correlation term. If x and t and y of t are changing independently, as I calculate this integral over a long period of time, this goes to 0. So if x and t and y of t are uncorrelated, then this is going to happen. X of t and y of t do not depend on each other at any point of time. Essentially, the product behaves like noise. The mean of that noise is going to be 0. And I get the covariance that is 0, right? So if they're uncorrelated, I calculate this, I just get the means out, right? All those small changes is going to be 0. The covariance is going to be this integral here. That is going to go to 0 if the two signals are uncorrelated. Why? Because you can expand it. You have the integral. If you expand it, you have the integral of xt yt plus mu x yt plus mu y xt. Those two cancel, mu x yt and mu y xt. Those two cancel. They're the same. Those two will give you minus 2 mu x mu y plus this other term mu x mu y. And if the first part is equal to that, the combination, the entire integral here will go to 0. We went through it a little bit of a confusing way. Just write it out and then you can actually see it for yourself. Okay? So if x and y are uncorrelated, then this integral is 0, and my sigma z is just given by these first two terms here. A squared sigma x squared plus b squared sigma y squared. Moving on, the root mean square of a signal is found from this integral. So basically, I look at the squared value of x over time, integrated with t going to infinity. I can estimate x RMS. It's an indication of how much energy you have in that signal. How much, rather, how much power you have in that signal. Okay. As you can see from here. So the signal power is usually proportional to that signal squared, the amplitude of the signal squared. The RMS value is the square root of that. So it's an indication of the amount of power available to you. And for a signal, any signal, you can show that the average power is proportional to mu x squared plus sigma x squared, right? So you have the DC part, the mean part, mu x, and the AC part, sigma x. Now a reminder, a Gaussian distribution, again from your statistics course, it was, or normal distribution, it was a distribution that was given by this expression here. Basically it gives you that bell curve. What that means is that, if you go away from the mean of a signal, the probability of signals with, large deviations from the mean is getting smaller and smaller, and it is symmetric around the mean value. How sharp it is depends on sigma. Where the mean is your mu. Why do we talk about this? Because there is a mathematical theorem, the central limit theorem, that says a lot of random phenomena, if you wait long enough, the distribution of the events can be described by a normal distribution. Noise is one of them. So we assume noise is a random signal whose distribution, amplitude distribution, is a Gaussian. It doesn't actually always have to be like that, right? So there are some noises that are not Gaussian, but for vast majority of cases, a Gaussian assumption for the noise distribution is just fine. Now, when we want to talk about noise and start analyze circuits with it or systems with it, we make a couple of assumptions. First of all, randomness. Noise has to be random. It should be unpredictable. From this point to the next point, you should not have a way of figuring out that it is going to go up or down. It is totally random. Noise also have zero mean, right? So if you average the signal, the top, the signals, the average, the ones that are above zero cancel the ones that are below zero, all those amplitudes and peaks, right? So you really, again, cannot predict where it is going. It's always going to have a zero mean. And lastly, it is a stationary signal, meaning that its statistical properties, especially the mean and the standard deviation or variance, do not change with time. Standard deviation is the square root of variance, if you needed a reminder. So statistically, this signal, we can take any portion of, let's say, its history, and if that portion of the history, if the window that we are taking, the time window that we are taking it, is large enough, it behaves the same. It always has the same mean, which is zero, and it always has the same variance, which is an indication of the amount of noise in your system. Okay. Now, if you look at a noise signal on an oscilloscope, you see something like what is shown below. But if you go and do a little bit of analysis and figure out, basically look at the amplitude of noise at any given point of time, you'll see that the distribution falls into something like that on the right side. Most of the signal, most of your noise has an amplitude that is close to zero, and then larger signals, something like this, are relatively rare events, right? So you don't see very large signals on the positive or negative side. Majority of the signal is actually focusing around your zero mean. And then we said, even though people are using the term noise for interference from the 60 hertz or things like that, they're not really noise. You can predict them. Once you measure them, once you know what is affecting your circuit or your system, you can go and cancel them, right? Or you can go and shield your circuit and get rid of them. So those are not noise. Examples of signals that are not noise are here. So induction from the power line. RF signals, when you're doing measurements, especially at higher frequencies, all these RF wireless signals around you are going to appear at the output of, for example, your amplifier circuit. Strictly speaking, they are not noise, right? If you know them, if you know the source, you can actually go and figure out exactly what you're getting and cancel them out. However, in some cases, it might be easier to just treat them like noise because you don't know the source and they can actually vary. But strictly speaking, they are not noise. Day and night effect on your circuit, that's not noise. Yeah, sometimes you have dependence on the pressure or light intensity or temperature, and that changes with time of day, but that's predictable. Once you figure it out and characterize it, you can calibrate it out. If you're using an internal combustion engine, you have spark discharge. Again, if you know the speed at any given point or the speed of the engine at any given point, you can at least know when it is going to happen. You may not be able to cancel it, but you will know when it is going to happen. Another differentiating factor between interference and noise is that interference is usually coming from outside. It's not created internally. And so here is how it's going to look like. So this is a signal where you have, let's say, low frequency signal, where you have a high frequency signal injected on top of it. So you see both of them together when you look at the signal on the oscilloscope. This is interference. If it were noise, it would look like this. So it's a random signal added to the top of your own signal. There's really no way for you to figure out how I can get rid of that. It's just going to stick there. Noise is always generated internally. Interference can be external or internal, but in most cases it is external, right? So it could be, as I said, the power line frequency and things like that. In time domain, noise looks like this. We have seen this a couple of times already, but if I only look at noise, and you can do this once you go to the lab and have an oscilloscope and just crank up the amplitude so that you can see tiny, tiny signals, you'll see this. This is what you see in time domain. Well, the mean is 0. There's no information there. And the absolute amplitude at any given point is a random number. There's really no value in knowing that the noise at this point was 1 millivolt. Doesn't help you, because that 1 millivolt of noise at this point doesn't tell you anything about what happens next or what happened before. The next voltage can be minus 10 millivolts, or it could be 2 microvolts, or maybe 0. So the instantaneous value of noise doesn't matter. What we should instead look into is, what are the statistical properties in the long term? When I look at this signal over a longer period of time, what happens? And that way, we have measurable quantities to compare this circuit versus this circuit, this output versus this output, this sensor versus that other one. So the mean part should be 0, doesn't say anything to us. The variance part is where we actually will have a measurable quantity to compare the performance of different circuits. We assume normally that the noise amplitude, this amplitude of your noise signal, follows a Gaussian distribution. And if you assume that you have a Gaussian distribution for your noise signal, experimentally it makes your life easy. Because now what you can do is that you can go and look at that signal on your oscilloscope. You can measure a band that includes 99% of your signal. So if I draw this band and 99.6% of your signal amplitude falls within that bandwidth is 6 sigma. It's 6 times your standard deviation, right? So basically, in a Gaussian distribution, it tells you that if you go 3 standard deviations from the mean on either side, the chances of seeing an event is going to be less than 0.5%. So very quickly, you can estimate the standard deviation of your signal or its variance from that simple measurement. Now, that's how you look at noise in time domain. Well, it's just a mess. In frequency domain, things can be a little bit easier. Now, what we do here is that we go and create a system. So we talk about power spectral density of noise in the frequency domain. Again, because noise are essentially spikes, right? So you have a spike of voltage, positive, negative. You can think of it as a combination of impulses or a series of impulses that you have with random amplitudes. And if you think about, what is the frequency representation of an impulse, we saw that, from the Fourier transform courses that you took before, an impulse has a white spectrum, meaning that it has all frequency components in it, right? So each one of those impulses produces all of those frequencies if they're fast enough, and that's the noise representation in frequency. So how do we characterize it? How do we quantify it? What we say is that we say, let's measure the noise power in a limited bandwidth. Well, let's define that limited bandwidth to be 1 hertz. We see how much power we have in that 1 hertz bandwidth. So let's say from 1 kilohertz to 1.001 kilohertz, I put a filter there, get rid of everything else beyond 1 kilohertz and after 1 hertz after that, and I measure the power of the signal in that 1 hertz band. That's called the power spectral density. So that gives me one number at that frequency, and then I move that filter across the frequency and I figure out what is the power at any given frequency. So that's the power spectral density. There are formal ways of calculating it. So the way that you calculate the power spectral density is that you go and calculate the autocorrelation signal, autocorrelation of the signal in time domain, and take the Fourier series from it. And there is a good amount of math involved, but conceptually that's all it is, right? So you take a 1 hertz filter, you put it different parts of the spectrum, you measure the amount of energy power that you have in that 1 hertz bandwidth, and then you go and scan it across the entire spectrum. Of course, the unit then becomes watts per hertz, right? So how much power you have in that 1 hertz bandwidth. You can use other units. So sometimes for convenience, I go and say, this is an electrical signal, this many watts per hertz in this kind of a configuration means this much volt. So I'm going to use volts per hertz, volts squared, for example, per hertz. Or if I want to get rid of the square value, I basically report the square root of that number. I say this many volts per square root hertz, right? But that's how I talk about how much noise I have in the frequency domain. Now, one interesting thing is that, for your signal that goes into a system with a transfer function of h j omega, you have an input spectral density, an output spectral density, and you can show that the spectral density of your input signal is shaped by the transfer function of your system. Don't worry too much about how these are derived, right? So I'm just going to make some introductions here and move into the calculations relatively quickly, just concepts. So again, the takeaway from this is that if you put a system in your signal path, the transfer function of that system, the frequency response of that system affects the power spectral density of your signal. That's expected. But how? Well, it does it through this expression. So if you have an input power spectral density, you multiply it by the absolute value of the transfer function squared, and you get your output spectral density. So if your noise that has a white spectrum, meaning that it has the same amplitude across the entire frequency band, goes into a system whose transfer function looks like this, this is what you get at the output. Your noise is not white anymore, right? So you have frequency components that have more noise than the other. So, and then here is another example. What you can do is that, for example, this could be your signal in time domain. this is your signal in frequency, same signal in frequency. This is like, let's say, an audio signal. You pass it through a filter, a band pass filter. This is what they used to use for landlines. On a landline phone, you basically have a 4 kilohertz limit for frequency. So they pass this through your band pass filter. Your signal will become a bit smoother. In time domain, if you look at it, you get rid of some of those sharp peaks. In frequency domain, if you assume it was relatively flat, the signal response was relatively flat, you essentially see a strong influence of your system at the power spectral density of the signal at the output. Now, the takeaway, or the other takeaway from this slide, is that the noise power, how much power you're left with at the output of that system, depends on this transfer function, depends on the bandwidth that is set by that transfer function. You may have a white noise going in, but this system truncates a whole bunch of that signal. In theory, your input noise had infinite power. In practice, after going through this system, you get a finite amount of power at the output. Same thing here, right? So this signal potentially has much higher power than what you have here. So remember this, the only way to reduce noise is to reduce bandwidth, to make your bandwidth smaller. For a constant input noise level, that's your only way of limiting noise at the output. It comes at a price. Lower bandwidth means that your system is slower. It may be harder to design and all that. But that's your only practical way to reduce noise. Anything else? You are not really doing it with the circuit. You can change something about the physics. You can go and say, I'm going to produce less noise to begin with. And for example, you can do that by cooling systems in many situations, right? So if you go and look at the literature, high-resolution cameras have a cooled image sensor. Right? By reducing the temperature, they reduce the noise. But once the noise is produced and it comes into your interface circuits and the rest of the electronics that you have, your only option is to limit bandwidth. So just keep that in mind. Attack it at the source, try to produce the minimum amount of noise that you can, and then later on your only option is to reduce bandwidth. Okay. Another way to think about it is that do not design an interface circuit, an electronic circuit, whatever, that has more bandwidth than necessary. Because the only thing that more bandwidth does to you is it increases the noise. Your signal is, let's say, a 10 kilohertz signal. Do not design a 1 megahertz amplifier for it, because that 990 kilohertz of extra bandwidth only adds noise to your signal, only destroys your signal to noise ratio, which is, by the way, defined this way. It's about the signal power over noise power. The signal power is proportional to, let's say, if it is a voltage signal, to V squared. So V squared divided by R divided by V noise divided by R. Well, V noise squared, the R's canceled, and it's about the power, right? So it's about signal power over noise power. You take the log of that, multiply it by 10, and that's how you normally report the signal to noise ratio. So this is your signal. You add some noise to it, right? So this is the noise. It gets added to your signal, and that's the output. If you look at it in frequency domain, well, you have your signal, which is in frequency domain just an impulse, if it is a single sine wave. You add noise to it. Noise is relatively flat in the frequency domain, and this is what you get, right? So at the output, you get your peak if your signal is larger than noise, and a floor for the noise. In time domain, you see it as these tiny spikes added to your signal. Now, different SNRs, this is how you can have a feeling about what different SNRs mean. At minus 10 dB, meaning that the signal power is 10 times less than the noise power, for a sine wave, you get something like this, right? So you can barely see a signal here, you can see that maybe there is some information embedded in that noise, but it's really hard. At 0 dB, when the noise power and the signal power are equal, you can start to see a signal. You can start to see some information is embedded there. 10 dB, yeah, it's easier now, and then 20 dB and so on. Larger values, you basically have almost no problem with noise, right? So if the noise power is 10 times less than your signal power or 100 times less than your signal power, you can focus on what the signal is telling you. Now, noise in electronics often limits the minimums for you, right? So if you're talking about communication signals, it tells you how far you can be from the transmission tower before the signal amplitude drops below the noise level of your low noise amplifier. If you're talking about sensors, it is the minimum signal that you can detect from your sensor before the noise of your amplifier buries it, right? So you're usually talking about something that is happening at the input. So what we do is that we usually measure the noise at the output of your amplifier or your system, where it is usually easier, right? You have less sensitivity to probing and things like that. And then go and figure out what was the equivalent input noise, right? So let's say, in a very simple case, I have an amplifier with a gain of 100. I go and measure the noise at the output of this amplifier. I say it is, let's say, 100 microvolt signal, the standard deviation at 100 microvolts. I go and say, well, it is as if I have a 1 microvolt noise at the input of that amplifier, which is then multiplied by the gain of 100. Why do I do that? Because it is the input where all the interesting stuff is happening. Why do I measure it at the output? Because it is the output where I have the easiest, let's say, time measuring anything, right? It's usually the output of a proper amplifier. So, but the interesting stuff is happening at the input. So your amplifier, you refer the noise of an amplifier to its input. Now, the good thing is that because it is showing at the input of the amplifier, the output noise of your sensor can be compared to it right away, side by side. So the output of your sensor, let's say, is producing a 1 microvolt equivalent noise. The input of your amplifier has a, let's say, 10 microvolt equivalent noise. This is much larger than your 1 microvolt. You have to change your amplifier. The amplifier is dominating the noise performance, and you go and fix that by, let's say, electronic design. So when you talk about the sensor system, this is how we characterize noise. We talk about the minimum detectable signal, sometimes referred to as resolution. The minimum detectable signal is that total noise that you measure at the output of your system, you know, electronics plus optical plus mechanical, anything that has come and gone through the system and shows up at the output, you measure that total noise divided by the sensitivity of your system that now includes the electronics and your sensor. And that is your minimum detectable signal. So if your output noise is, let's say, 1 microvolt, you're measuring, let's say, the output of an accelerometer whose output is 1 volt per G. Let's say that's the sensitivity of the electronics and MEMS combined. You can say that the equivalent acceleration, the minimum detectable signal at the input that would produce that 1 microvolt is 1 micro G. So 1 micro G is going to be my MDS, my minimum detectable signal. A related issue is dynamic range. It's usually the largest signal that you can measure divided by MDS. So minimum detectable signal is usually determined by noise. If, you know, sometimes it's the digitization part that messes your work up, but it's usually noise that limits it. And then at the high end, it's sometimes the limitation from linearity of the amplifier, sometimes it's the power supply, all those things. So you have a maximum for your signal and a minimum for your signal. The minimum is set by noise, and the minimum is usually where you pay more to reduce it. So let's talk about a few different types of noise. The first one is the thermal noise. All of you by this point in your education, I think, have heard that resistors produce noise. Resistors are noisy. And this is why. Or this is how we model that, right? If you have a resistor, you go and so let's see what happens inside this resistor. So you have a piece of resistor, let's say like this, a long resistor. You pass current from one end to the other and you measure voltage. That's what a resistor does. If you keep this resistor floating, internal structure of this resistor, it's a conductor, you have a bunch of electrons. These electrons are moving randomly, right? So at any given point of time, it's not a perfect distribution. You will have a little bit of electrons, let's say that more electrons on the left side of this than the right side, or the opposite, right? And as soon as that happens, you have an electric field across the resistor. This random motion means that you get a random electric field or voltage across your resistor. How much is that voltage? Well, you can estimate it from this expression here. This, I use it as a voltage source. I can model it using a voltage source in series with my resistor. Now this resistor is ideal and noiseless. All the noise is represented by this voltage source. I am talking about the variances here. Remember, this is random numbers. So it's positive, negative, and random in all cases. This is the variance of that noise. It's not the magnitude of the voltage. It's the variance of that voltage. And the variance of that voltage is, or voltage source is given by this expression. What are these parameters? Kb is a physical constant, Boltzmann constant. T is absolute temperature, and R is the resistor value. So the higher the resistor, the higher the noise. The only way to reduce this noise is to reduce the temperature. If you have to deal with a 1 megohm resistor, your only way of reducing noise is to make the temperature close to 0 Kelvin, which obviously is neither easy nor cheap. So this is the power spectral density, volts squared per hertz. I can go and come up with an equivalent, let's say Norton equivalent of that circuit. I can take this voltage source and put it in parallel with the resistor as a current source. In that case, the variance in that current is given by this expression here, right? So for kBT, the value is going to be divided by R. Once you square it, you get R squared here in the denominator. That cancels, one of them cancels the R in the numerator, and then you get KB, 4 kBT divided by R. So the only way to limit that noise or to reduce that noise is to cool down your resistor, or notice the unit here is volts squared per hertz, so reduce the bandwidth of your measurement. If this is the power spectral density, right? So if you want less noise at the output, cut that bandwidth into a smaller piece, and you get rid of that noise accordingly. But within that bandwidth, 4 kBTR. So if you want to reduce that, if you have a fixed bandwidth, your only option is cooling the resistor, which is, again, not easy. This thermal noise is also known as Johnson noise or Nyquist noise. So these are people that initially did the calculations and derived the equation that we saw here. Interestingly, you can drive this equation using both quantum mechanics or classical physics. So there are two different approaches to solving this statistical problem, but both of them will get you to the same result. So look it up if interested. So how do we do noise calculation? So let's say if I have one resistor, no problem, I know the noise. But if I have two resistors, then what do I do? So remember that I can go and model the noise as a series voltage source. I know the variance of that voltage source, but nonetheless it's a voltage source. So let's just go through this calculation together relatively quickly. So what I'm going to do is that I'm going to draw those two noise sources for the resistors in my model. So because the value of the source, it's a random source, I don't put plus and minuses across them. And actually by putting a cross in there, I'm just indicating that this is not a regular voltage source, it's a noise source. So I don't have plus and minuses here. They don't really mean anything. So let's say this is R1, R2, and I want to estimate the total noise at the output. So let's say this is V in and this is V out. But if I'm talking about noise is generated internally, so I'm only looking at what happens between the two resistors. V in is really not a problem. So I can assume that V in is ground as well. So this is Vn1 and this is Vn2, and I know that Vn1 is, squared Vn1 is 4 kBT R1, and Vn2 is 4 kBT R2. Okay? Now, what is the noise at the output? What if I'm measuring the noise at that node labeled output or V out, what do I measure? I look at this, if I consider the noise sources to be voltage sources, I can use superposition. Everything here is linear. So what I can do right away is that I can show that V out is applying Vn1 times R2 over R1 plus R2 plus Vn2 times R1 divided by R1 plus R2. Okay? So if these two were normal sources, that would be the output, and then I'd be done. However, these are not regular sources. This is noise. So I really cannot talk about instantaneous amplitude. I need to go and calculate the variance of this signal. So if I go and calculate the variance of the signal, I'm calculating, let's say, V out at any point in time minus its average. But because the V out is produced by two noise sources, the average is going to be 0, right? So V out minus 0 divided by 2 from, let's say, 0 to t, and 1 over t, and limit of this as t goes to infinity. I need to calculate this expression, right? And then I can see that it's going to be if I use this equation that I calculated in the above, it's going to be R2 over R1 plus R2 squared times Vn1 squared, Vn1, there's no squared, plus R1 over R1 plus R2 times Vn2, this whole thing squared dt. All right? So now I can go and expand that. So I'll go and expand that, and it becomes, so this is equal to t to infinity 1 over t d square, the integral of that expression squared. So R2 over R1 plus R2 squared Vn1 squared plus R2 over R1 plus R2, R1 over R1 plus R2 squared Vn2 squared plus the product of the two, so R1, R2 over R1 plus R2 squared times 2, Vn1, Vn2, the whole thing dt. Okay? So far so good, right? Nothing complicated. But now that I want to expand this or calculate this integral, I take advantage of the fact that these two are two different resistors. So the noise that is produced by one is independent of the other noise. The two Vn1 and Vn2 sources cannot be correlated. They are independent noise sources. So The first term and the second term are easy, they stay, but the third term, when I calculate that integral, this term here, because Vn1 and Vn2 are independent from each other, it should integrate to 0. And then once that integrates to 0, once that one is gone, I don't have to worry about this anymore. I have the integral of the first term plus the integral of the second term, Vn1 squared, Vn2 squared. I already know those. So the variance of Vn1, I know it. The variance of Vn2, I know it. I just multiply them by the coefficients in front of them. So let's just do that. So once I calculate the integral, evaluate it, well, this term is just the coefficient, so it's R1, R2 squared divided by R1 plus R2 squared times Vn1 squared. What is Vn1 squared? It is 4 kBT R1 plus R1 squared over R1 squared plus R1 plus R2 squared times 4 kBT R2. Okay? And therefore, I can factor 4 kBT. I have R1, R2 over, let's say, R1 plus R2 times R2 okay, I just factored R1, R2 out, and for the denominator R1 plus R2 squared, I just kept one R1 plus R2 squared. R1 plus R2 squared, I kept R1 plus R2 behind the brackets and one R1 plus R2 inside. And then, you can see that now this term, this is 1, and all I have is this. So this is going to be 4 kBT R1, R2 over R1 plus R2. Okay? So that's the standard deviation, the variance of the signal at the output of that circuit. What does that mean? Well, look at that circuit. I have R1 and R2. If there were noiseless resistors, if they were ideal resistors, you could see that I had R1 in parallel with R2. We went through all this calculation. Look at this combination. This is R1 in parallel with R2. Okay, so the noise, VO noise squared, is 4 kBT times R1 in parallel with R2. I could have made my life easier if I knew this from the beginning, that the noise of a resistive network at the end of the story is equal to the noise of the equivalent resistance of that resistive network. So if you have a complicated resistive network, just go and simplify it first, then calculate the noise of that network. It's usually much, much easier. The other thing that I noticed is that, when I'm calculating the effective noise of these, let's say, independent noise sources, any cross-product term will be 0. So at the end of the story, it's as if you're calculating the noise of the first one, the second one, and you only keep the squared terms, the variances at the output. Any cross product will go away. But again, the takeaway here is that the noise of or the equivalent final noise of your circuit, your resistive network, is the noise of the equivalent resistance. And we have the same result here for your reference. So that's thermal noise for resistors, but we have other electronic noises. Another one that is fairly common is shot noise. This is a noise that is produced when your charge carriers have to jump over a barrier. Right? So they come, they hit a barrier, and then randomly, if they have enough energy, they jump over that barrier. When does that happen? Well, inside any diode, you have that barrier. So if you go back again to what we learned from electronic courses, the depletion region in a diode creates a barrier that basically slows down the movement of the charges between the two sides of the junction. If one electron wants to jump from one side to the other or hole, they have to overcome this barrier that is created by the depletion region. So, because this is random, you know when they will have enough energy to jump over that barrier, you will get a change in that current through the diode. The magnitude of this change is proportional to the DC current. Right? The more current you pass through that diode, the more you will have of these charge carriers jumping over the barrier. So it doesn't mean that your noise has a DC value. The DC value of the noise, or the mean value of the noise, is 0. But once you pass a current through that structure, through this diode, the shot noise, the variations in that current, right, the variance of the current is proportional to the DC value, and of course the charge of your charged particles. Again, this is the power spectral density. The unit is amps squared per hertz, and the model is like this. So you put a shot noise source in parallel with your transistor. Shot noise is a white noise, meaning that you have a flat power spectral density for it. And this is the implication of shot noise in a situation that a lot of you have seen. If you go and reduce the shutter time, you take a camera with a digital image sensor, and you go and play with how long your shutter is open, you get the result like that. So a really fast shutter opening time versus a very slow shutter opening time. Over here, what happens is that you give the sensor enough time to average out the noise. Over here, you basically do not have enough signal, it's just noise. And you see that graininess in the image. That graininess mostly comes from shot noise. Okay, another type of noise that you see in electronic systems, and this one is a little bit more annoying than the rest, is flicker noise. This type of noise, the property of it is that the noise power increases with 1 over f, and maybe f over beta. F is frequency. So the power spectral density has a positive slope as you go to lower and lower frequencies. It looks like this, right? So your thermal noise and Johnson noise and shot noise and all those other ones have a flat frequency response. The 1 over f noise looks like this. As you go higher and higher in frequencies, you basically don't see that. But at low frequencies, that is going to dominate, right? So you might say, okay, great, so I only operate at high frequencies. Why would I care at low frequencies? Here's the problem. A lot of the sensing applications are happening at low frequencies, right? So you're dealing with signals that are not too fast. This corner frequency, where you basically have a transition from seeing mostly 1 over f noise to mostly thermal noise, for transistors that you use in electronics is typically around tens of kilohertz to maybe kilohertz range to hundreds of kilohertz range. So it covers a lot of the band that you actually would want to use for sensing. And unfortunately, the noise power becomes larger and larger at lower frequencies. It's also known as pink noise. If you think about optical spectrum, red signals are at the lower end of the spectrum, lower frequencies. Blue and violet signals are at high frequencies. So we call it a pink noise because you see it dominantly at low frequencies. The challenge with flicker noise, as I said, is that for slow measurements, DC measurements, this is your pain point. And because it is noise, there is no way around it. Your only solution is to go and use a better device, better circuit. You cannot really limit it. Good news is that it's mostly an electronic phenomenon, right? So your mechanical systems don't exhibit flicker noise that much, or a measurable flicker noise. So let's assume that in an electronic system we figured out the noise sources. How do we represent them? Well, resistors are the only ones that produce noise. Remember, noise was associated with dissipation of energy. Capacitors and inductors do not dissipate energy, so they do not have noises. So for resistors, this is how we show noise. Amplifiers have, let's say an op amp in this case, have a combination of transistors and resistors inside them, right? So you see the collective response of all of those, noise response of all of those components at the output of the op amp. But we said that normally we would like to refer the noise to the input. It's an easier place to compare noises, let's say from this system going into this system. If I know the noise here and noise the input of this system, it's easier to compare these noise levels. So I would like to bring those noises to the input. For an op amp, I do it like this. So remember, the transistors that you have here have shot noise. The resistors that you have here have thermal noise. The transistors also have flicker noise. Different components have independent noise sources. And then what we do is that we go and measure the noise at the output and try to represent that output noise with noise signals at the input. Usually you associate one current noise to either one of the two inputs, a noise source to either one of the two inputs. They're usually of equal magnitude, and only one voltage source is used to represent the amplifier noise at one of the two inputs. Again, it doesn't matter which input you use. You put this voltage source at the input. That makes your circuit analysis easier. You have to include it, but you put it where it makes your life easier. And we'll go through one example to see how. The current sources have to be at both inputs. The good news is that the current sources in most cases can be shorted out. Now, when you have these noise sources, again, the cross products don't matter. They cancel out. It's noise powers, or the power of the signal at the output because of each one of these sources that adds up. And if you have a multi-stage amplifier chain, you usually have to pay a close attention to the noise from the first stage, because that noise will be amplified by the first stage, goes into your second stage, goes into the third stage, and so on and so forth. We'll see that an example in a second, but usually you focus the most of your noise, let's say reduction efforts, on the very first stage in your electronic circuit chain. For those of you who have played with RF systems a bit, you know that there is an LNA block that you put very close to the antenna. This is the low noise amplifier block that you put very close to your antenna, and then after that, once your signal is a bit stronger, you can maybe transmit it over a bit of a distance through a cable, or start playing with it, start demodulating and filtering and all those other things. Okay, so calculations of noise is an example. So we have a transimpedance amplifier that we saw we can use to measure current. The current source in this case is a photodiode, so we're basically measuring an optical signal in the environment. But because it is a photodiode, it will produce noise. It will have an associated shot noise. I have an op amp to amplify this signal. The op amp will have its own noises, and then in order to convert the current to a voltage, I'm using a resistor which has its own noise. So what I want to do is that I want to figure out what is the output noise in this circuit. So let me draw that circuit, including the noise sources. I had a diode. This diode has a short noise source in series with it. It goes into an amplifier, so this is my transimpedance amplifier. I have a current noise source here for the amplifier, another current noise source here for the amplifier. So, and this is grounded. I need to put my voltage noise source for the amplifier either at the negative input or the positive input. I'm going to put it here, and you will see soon why I prefer it here. So this is VNA, this is INA. Maybe I put a squared on top of this so that I know these are noise sources. So this is IND squared. And this goes through a resistor. So for the resistor, what I do is that I'm going to use an equivalent current source here instead of I can put a series voltage source, or I can put a series current source, a parallel current source. And again, I'll tell you why I do that. Or doesn't really matter. Okay, so I have a bunch of noise sources here. Each device has at least one noise source associated with it, but they are independent. So what I can do is that I can calculate the power of the noise at the output for each one of these and add up those powers. So instead of calculating this circuit with superposition and trying to figure out which cross products go away and all that, because I know the cross products will go away, what I can do instead is that I can look at these individually, one at a time, calculate the effective output power because of that source, and then add it up with the rest of the components, or the noise from the rest of the components. So for example, if I go and look at this source at the very beginning, so let's say A, V, N, O, let's just call it D for the diode squared. So the voltage at the output is going to be VNOD. It's going to be this ID, IND, the noise from the diode times, well, there's no noise, no current going in, all the current goes through RF to the output, so it's times RF. Okay, so that's the output voltage noise because of that input current noise. I know that I cannot talk about the amplitudes, so what I can see is that VNOD squared, this is the power, is IND squared RF squared. That was easy. So B, I go and look at, let's say, the effect of this current noise, current source at the output. However, right away I notice that if I'm using superposition and if I'm looking at these noise sources individually, well, if this VNA is 0, then my current source is shorted. So it does not really produce any signal. So this one doesn't produce any signal, so let's just call it INA2. This is INA1. So that one doesn't do anything to me. Great, I got rid of that. But VNOI, due to this resistor, this top one, has to be calculated. So ignoring all the other current sources, and then the diode is reverse biased, so open circuit. This current doesn't go into the op amp, it goes through RF and shows at the output. So it's going to be INA. It's INA1 and INA2 are usually equal, so I'm just going to say INA times RF. And therefore, I can see the noise power at the output is going to be INA squared RF squared. Good. So I took care of the current source as well. Let's deal with that VNA part here. So C, VNA. So VNOA, let's say the voltage for your amplifier. If I apply that source and get rid of the other sources in my circuit, at the end of the story, I'll see that I have an open circuit here. It's a non-inverting amplifier. I have an open circuit for the resistor feedback, the resistor that was connected to ground, and therefore the gain of the op amp the gain of the circuit is going to be 1, right? So it's going to be just VNA, or VNOA squared is going to be VNA. Whatever your amplitude, your input signal amplitude is, that's going to add up, show up at the output. So that was easy as well. And finally, the effect of the noise from your current source in parallel with your RF. Again, I zero all the other sources here. If that's the case, I will have a virtual ground at this node, and the voltage produced here at the output is just this current times RF. You could have used the voltage source in series with RF, and in that case, because the current in the loop is 0, you could have seen that that voltage shows up directly at the output. If you do it this way, let's say VNO, let's just say R, is just going to be INR times RF, and therefore again we see that VNOR squared is INR, whose value for the resistor we at least know is 4 kBT over RF, right? Squared times RF, which is your 4 kBT RF, right? And that's it. So to calculate the total noise, you add up all these powers, so it's going to be, so VNO total, or VNO total, is going to be this plus this plus this plus this, the sum of these 4. Okay? And that's the end result. Now, once you have a circuit like this, you can actually go and start looking into which noise source is more important. If you want to minimize the noise at the output, this expression here now lets you compare the effect of the amplifier noise, the current noise from the amplifier, to, let's say, the shot noise from the diode. This one you may not have a choice. Maybe you are basically given a sensor and you have to use it, but you can play with the values here. So you want to use an amplifier, for example, right away, where the input current noise of that amplifier is much less than the shot noise of your diode. If not, this is going to dominate and you're going to basically bury your diode noise. Well, once you go past that, you want to make sure that the voltage noise of your amplifier is not dominating. So again, you can compare it with these and also make sure that the voltage noise of RF is not making your life harder, right? So once you basically have an expression for the output noise, you can go and figure out where is some room for improvement. Here is another example. You have a chain of amplifiers with their own noises. So in this case, let's just assume we have a voltage noise in series with each amplifier, and we want to know what is the total noise at the output. My suggestion to you is to go and write it out. That you assume that you have a voltage noise Vn1 in series with G1, Vn2 in series with G2, and Vn3 in series with G3, and calculate V out at the output. If you do it right, this is the expression you should get. What you will see is that at the output, the total noise at the output is going to be the gain of the 3 amplifiers times the noise of the first one, the gain of the last 2 amplifiers times the gain of the second one, and the gain of the third amplifier times the noise of that amplifier. All these gains are usually much larger than 1. So what immediately it tells you is that the noise, the total noise at the output, is dominated by the noise of the first stage. If you want to have a low noise amplifier, go and make this as small as possible. Because whatever that noise is, it is multiplied by the gain of the entire chain. The second stage it's less gain, right? So 10 times less, 20 times less than the first state. And that is usually a huge relieving factor. Okay. Now, we said energy dissipation brings with itself a noise source. Well, what about mechanical systems? At macro scales, we often do not concern ourselves with noise. We basically are more concerned about the energy dissipation and Q. Micro scales, well, if I want to combine the MEMS device with an electronic circuit and so on and so forth, I want to be able to combine them with each other. And I need to go and figure out how much noise I'm producing in the mechanical domain and compare it to the noise in the electrical domain. So what is the energy dissipation here? What represents energy dissipation? It is this damping factor, this damper that I have in my system. Zeta here represents linear damping. Well, that's a lot of a good level of simplification. Even typical friction is not following that model, but at MEMS scales, where we usually deal with viscous damping and those kinds of things, that actually is a good model. Types of damping at microscales include viscous damping. When you want to move a mechanical structure, you have to overcome, let's say, the air resistance. Microscales, you have to do the same thing. What happens there is that there are two problems that you have to deal with. One is the sliding of this piece in air, in gas. So you have to overcome that force, that friction. The other one is that, which happens a lot in MEMS because of the capacitive interfaces, is that as you push these two electrodes towards each other, you have to push the air between them out. Or when they're moving away from each other, they're going to suck the air back into that gap. That is a dissipation, energy dissipation mechanism. You're squeezing the film in and out of that gap. So it's called squeezed film damping, but it's type of a viscous damping. You're basically dealing with the fluid movements, fluid interactions with your solid structure. Your only way to avoid it, obviously, is to operate under vacuum. If you get rid of the fluid, you get rid of viscous damping. Fluid in this case is gas. Another source of loss is anchor losses, and this happens in structures where you have vibrations. So something is going back and forth, like in your resonance sensors, and you assume that this boundary condition is fixed or whatever that you assumed it is, but as it is in practice, you're basically going to deflect the anchor point a little bit here. Right? So this is your resonator going up and down. Your substrate here is not as rigid as you assume in your model. In practice, you're going to bend this substrate up and down. What is happening is that this point, this contact point to the substrate, behaves as an acoustic source, right? So it radiates a little bit of your vibration energy into your substrate. How much of it? Well, it depends on your design, but it can be significant. In most situations, viscous damping is the first one that you have to worry about. Once you get rid of viscous damping, let's say by operating under vacuum, anchor losses become visible and the second source of loss to deal with. Another one is thermoelastic damping. Again, this is happening in vibrating structures. So you probably have seen this so far. If you take a plastic ruler and somehow fix one end of it to something and try to bend it up and down many, many times, repeatedly. And after a while, if you touch where you were bending, you will notice that the temperature has risen, right? The mechanical energy that you used here to produce strains and stresses, those strains and stresses, some of it, a little bit of it has converted into heat. Once it converts to heat, it's gone. It's lost. So thermoelastic damping is that source of damping. Your strains and stresses through internal mechanisms happening at the boundaries between the crystals and amorphous materials and all that turn into heat. It's internal friction, right? And that again is energy lost, so therefore it's a source of damping and therefore it produces noise. You may have surface losses. This is the losses that happen at the surface of the material because of the interfaces that you have with the environment. You can have surface tensile forces or compressive forces because of the films and how they react to the environment. But At the end of the story, all of these losses, we just combine them and represent them with one zeta. If you're lucky, we can do a good job on that. Some of these are easier to simulate than the rest. Some of them you need measurements. But at the end of the story, you can combine all of them and put a zeta number there that includes the effects of all of these. Once you do that, you can show that in your mechanical system, that damping represented by zeta produces a noise force as given by this expression here. And you notice that this is very, very similar to what we had for the resistors. Why is that? Well, in case of a resistor, in case of a Johnson noise, the thermal noise that you had was because of the random movements of electrons in a piece of a conductive material, and it produced a random field across it. In case of mechanical systems, it's those air molecules that are impinging on your substrate, for example. And that impingement of air molecules onto your proof mass, for example, in case of an accelerometer, that's the force. That's this force that, statistically, this is going to be its variance. Now, once you have a mechanical system and you figure out what the damping is, you can go and calculate this noise force. Once you have the noise force, you can calculate the response of your system to that noise force and figure out what happens at the output. Here is an example. So this is a multi-domain noise example. I will go through this quickly. I'll tell you how to solve it. We'll go through the full solution during a live session if you guys and gals would like it. But how do we deal with a noise problem like this? So the first two parts of this problem are easy. What I have is a piezoresistive accelerometer. I have a proof mass. I have 4 beam springs connecting this proof mass to the substrate. I've seen this device before. Once I have an acceleration, it beams in, let's say, what direction is that? Z direction. And when it moves in Z direction, up and down in Z direction, it produces a stress at the corners where these beams are connected to the substrate. If I put my piezoresistors here at that base, I'll get a change in resistance proportional to that stress, which I can relate to the displacements of the proof mass and therefore the acceleration. So that's how it works. So the first part of the question, what I have here is that I have the resistor values. Notice that I have longitudinal resistors as well as these transverse ones. And I use them because my piezoresistive coefficients are opposite. For transverse ones, it's the opposite of the longitudinal ones. So what that means is that if this piece goes in, if this piece goes in plane, so in this case going in plane, or in this case coming down, I have a tensile stress at this location and this location. R1, because pi xx is positive, R1 will increase because of that stress. R3 in this case will decrease because it has a negative piezoresistive coefficient. So I have 2 resistors that are changing in opposite directions. Life is made easy because the values of the resistors are given to be the same, and so are the piezoresistive coefficients. Now the first part of the question says, arrange these resistors in your Wheatstone bridge so that you get the maximum sensitivity. This is not noise related, this is about resistive measurements. Well, I know that if I want to get the maximum sensitivity out of a Wheatstone bridge, I want to arrange the sensitive elements in there such that they move in opposite directions. The movements or the changes between the elements are opposite. So if R1 is here, I want a device here whose value is changing in the opposite direction for the same input. So R1 here, I need to put either R3 or R4 down here. And then next to it should be the one that increases, so this is going to be R2, and again, whatever that is remaining up here. So when you go through this Wheatstone bridge, you have to alternate. One goes up, one goes down. One goes up, one goes down, right? That's how you ensure the maximum sensitivity. The second part of the question says, what is the sensitivity of this device? dV out over dA in. Well, again, we have solved a similar problem before where you displace the proof mass, you estimated the stress, do the same thing, multiply that stress by the piezoresistive coefficient, you get delta R's, and put them in the formula that we have for the Whitson bridge, you get your delta V out as a function of input acceleration. Again, if you want, we go through the full solution during the live session. Finally, and importantly, what is the minimum detectable acceleration for this device? So we get rid of all the sources, signal sources here. We want to see what is the noise that shows up at the output of this accelerometer output without any input. And normally a signal to noise ratio of 1 is your limit, or the minimum detectable signal. When they talk about it, it is about what is the noise that you have produced. And we say a signal that has the same amplitude is your minimum detectable signal. So to solve that, let's just have a look at representations of the noise here. Okay, so I have a mechanical device. That mechanical device is, I have the Q for it. The Q was given. So what I can do is I can go and calculate zeta based on the value of Q. Okay? Once I calculate zeta, I can calculate M, I can calculate the resonant frequency, and I have Q. Once I calculate zeta, I can go and calculate the noise force. Okay? So that's the noise force. So this noise force is affecting my accelerometer. Well, this noise force, if I want to figure out how much is the equivalent acceleration, what I can do is that I can go and divide it by the mass. And that is my equivalent acceleration noise. If I use this expression into here, I can see that this noise force is 4 kBT m omega naught over q. One of those m's cancel, so that's that. That's the equivalent input acceleration. Now the point here is that, how much is this comparable to, let's say, the noise that I produce because of the resistors in my Whitson bridge and the amplifier. So if I look at those, what I have is, let's say, a Whitson bridge. I have each one of those resistors has its own noise source, right? And then I'm measuring these with an amplifier. The amplifier itself has some noise. So let's call this R1, R2, R3, R4, and this is, let's say, VR1, VR2, and so on and so forth, right? And I can go and solve this and figure out what is the total noise that the output is, and maybe divide it by the noise of the amplifier and come up with an equivalent noise here. However, what I also can do is remember that the noise of a resistive network is equal to the noise of the equivalent resistance. So I can right away simplify this. So I can put, let's say, this is my amplifier. Let me put my amplifier noise source here. This is where I'm measuring it. And on each one of these inputs, I combine the two resistors. So let's say if, let me see if I should put R1 and R2 like that. No, this is R3 here, and let's say R2 here up high for the Whitson bridge to be the maximum provide maximum sensitivity. Okay, so then what I can see is that, so I can put R1 in parallel with R3 for this branch, and its own noise source. So let's call it this VNR13, and same thing here. So this is VNR24, and this is R2 in parallel with R5. So only 3 noise sources left. I go and calculate the output noise here. So VON total at the end of the story, you can show that it's going to be, if the input current to your amplifier is 0, there's no voltage drop across this or across this. So it's simply going to be VNR13 squared times the gain of this amplifier squared plus VNR24 squared times the gain of amplifier squared plus VNA squared times the gain of the amplifier squared. If you wanted to figure out the equivalent input noise, VNI, let's call it, squared is that divided by the gain of the amplifier. Once you divide those by gain, it's just going to be VNR13 squared plus VNR24 squared plus VNA squared. Okay? So that's the electronic noise. You can calculate the mechanical noise right here. You have the sensitivity of the system. So what you can do is that you can say this much equivalent acceleration produces this much noise at the output. You can bring it back to the input of the amplifier, or you can keep everything at the output and compare and see how much the total noise of your system is. And that's the noise calculation, right? So it looks a bit complicated, it looks a bit challenging, but in most cases you can, first of all, simplify your circuit. If you can combine resistors and come up with, equivalent resistances that are parallel, series, all those things, do that. Remember, you can use superposition. At the end of the story, these are voltage sources and current sources. You can apply them one at a time, but it's the powers that add up. So what you can do is that you can apply a superposition, apply one noise source, calculate the output noise because of that, square it. You're talking about powers now. Then the second one, then the third one, then the fourth one, and then you add them up, add the powers up at the output. So here is a question for you to think about. If I have 2 equal resistors in series, what is the output noise? How much the output noise voltage, if I look at the standard deviation, increases if I put 2 resistors on top of each other? Hint, power is twice, but what about the voltage? And that's basically how you do the calculations. Now, remember, these numbers are power spectral densities. At the end of the story, it is voltage squared per hertz. So you need the bandwidth information. You need to know how much is the bandwidth of your system in order to calculate that as a voltage squared number. In this case, I think it was told that the bandwidth is limited to the resonant frequency of the structure. So once you have the K and the M, you can calculate the bandwidth and multiply this number V squared per hertz by that bandwidth, and you get a V squared value for the variance of your signal. Now, so that's how you do the calculations, and as I said, we can go through the numbers during a live session. The last bit I want to talk about is essentially your only hope of doing a low noise measurement inside a noisy environment. Once your noise is produced and you have to deal with it. If you have the option of cooling down the source, maybe you can do that. But once the noise is produced, how do we deal with it? Throughout the whole discussion here, we saw that you're talking about power spectral density. Your only way of reducing that noise power is to limit the bandwidth. So the technique that we use here is called synchronous demodulation. It's a nonlinear measurement technique. What we are doing here is that we have to deal with 2 problems. One is that if I want to do a measurement on this system, I need to limit the bandwidth, right? So let's say my system in theory has, let's say it's a photodiode, right? It has unlimited bandwidth practically for whatever amplifier that I'm putting in front of it. But I don't need all that bandwidth. So first thing I do is that I go and put a low-pass filter in front of it. The second problem I have right away is that the low-pass filter, I have the 1 over F noise. So if I put a low-pass filter in front of this circuit, the 1 over F noise will kill me if I'm only interested in in the lower portion of the frequency. So this is the setup that I use. This is how I deal with this challenge. What I do is that I go and take my device, I feed it with a reference signal, and I measure the signal at the output of it. At this end, the output of this device under test, well, it's a linear device, will have an amplitude and phase difference depending on what I feed into this signal. I take the same signal and pass it into here. I apply it to a mixer. So let's say if your device under test is, let's say some sort of a test device, let's say a capacitor. You take the signal, let's say at 1 megahertz, apply it to your capacitor, get this signal over here, and take the same signal and apply it to a mixer. A mixer multiplies the two signals by each other. So what happens at the output of that mixer, you have a sine wave through the top branch, you have another sine wave through the bottom branch. You get two components here. You get sine omega t squared, so you will have, let me see if I have the equations. You have Vref sine omega t, this is your input signal. This is the signal after your device under test. The mixer signal is going to be the product of the two. You have two sine waves of the same frequency multiplied by each other. What happens is that you can basically divide it into two components, a DC component plus a component at 2 omega t. The low-pass filter here will go and keep the DC component, which is this number here. Now, why do we love this? We love this because the bandwidth of the measurement is set by the low-pass filter you have over there. So it's very hard, let's say if you're measuring a signal at 100 kilohertz or 1 megahertz, it's very hard to have a bandpass filter, let's say, whose width is only 10 hertz. It's really difficult to make such a narrow band filter at high frequencies. But a 10 hertz low-pass filter is not a big deal. So what I can do is that I can go and multiply the reference signal with the output signal of my device under test, convert some of that information back to low frequencies, and cut it off with a low-pass filter. This technique is called synchronous demodulation. I demodulate the signal from the device under test using the signal that I use to excite it. So the two are synchronized. And I get the amplitude information this way. If I want to get the phase information, what I can do is that I can rotate, I can delay this signal by 90 degrees or have a phase shift of the reference signal by 90 degrees using a second mixer. I get a second component that is proportional to the sine of the phase difference. So I have the cosine of the phase difference, I have the sine of the phase difference, and I have an amplitude component. And with the two of them, I can get both amplitude and phase information. This is your only technique to measure low noise measurements with very small bandwidth, and it's used extensively in a lot of test instruments, and if you want, you can actually implement it using relatively simple digital and analog electronics as well on board. Some of these functions, like the mixing, like the filtering at the end, can actually be done digitally. So that's that for the noise and interfacing section of the course, and I'm going to post an assignment soon so that you have some, let's say, warm-up questions. And then after this, we're going to talk about signal processing for these micro devices. Until then, take care and stay